So we have a very long lecture today. So today's lecture will be covering symmetric matrices, then positive definites, and SVD, singular value decomposition. So there is this symmetric matrix is a special case when you do the diagonalization. Okay. So what is special when ax equals to lambda x? So ax equals to lambda x. So what special happens when A is equals to A transpose? So the key factor of being A equals to A transpose is basically the symmetric matrix. The symmetric matrix has only real eigenvalues, and the eigenvectors can be chosen orthonormal. So if you could remember what this term orthonormal means, it means that the vectors are perpendicular to each other, and the value of the vector is 1. That means those are unit vectors. Okay. So in case of symmetric matrices, this n for n by n matrix, this n orthonormal eigenvectors go into the columns of S, and every symmetric matrix is basically diagonalizable. Okay, so the eigenvectors of the eigenvector matrix of S becomes Q. So in case of Q, we read in the chapter of orthogonality that this Q is a spatial matrix where the columns of this matrix is spatial because it has the orthonormal vectors. That means all the vectors inside this matrix is perpendicular to each other. So in case of symmetric matrix, we read in the previous class that A can be diagonalized as S lambda S inverse, right? So in case of symmetric matrices, so in case of symmetric matrix, this A becomes, so this S becomes Q, so it becomes Q lambda Q inverse. But in case of symmetric matrices, we know that Q inverse, in case of, so these are orthogonal vectors. In case of orthogonal vectors, we know that Q inverse equals to Q transpose, right? So A can be written as Q lambda Q transpose. So this is a very special case in case of symmetric matrices only. Okay. So this is known as the spectral theorem. So the spectral theorem is basically spectral theorem. Rafael.
Could you explain it again?
Which one? Which part?
From this S equals to Q.
S equals to Q. Oh. Do you remember this S matrix? What what this S matrix means?
Yes, it is a matrix of the eigenvalues.
It is a matter of eigenvectors, right?
Yes, sir.
So in case of symmetric matrices, in case of symmetric matrix, when we diagonalize it, so we choose the eigenvector in such a way that those eigenvectors would be orthonormal. Okay, orthonormal means all the vectors would be perpendicular on each other and the values are normalized. So that means those would be unit vectors. So
Yes, sir, got it.
if I put those column vectors inside a matrix, that matrix would be an eigenvector, right?
Yes, sir.
So we can write S lambda S inverse as Q lambda Q inverse. And if you could remember the chapter of orthogonality, we knew that orthogonal vectors had this very special characteristic of Q inverse equals to Q transpose. So with that, we can replace this Q inverse with Q transpose. Thus this equation.
Yes.
So this spectral theorem says that every symmetric matrix has the factorization with factorization A equals to Q lambda Q transpose with real eigenvalues in lambda and orthonormal eigenvectors in S equals to Q. So this is called the symmetric diagonalization, when the symmetric diagonalization. So the symmetric diagonalization is basically A equals to Q lambda Q inverse. So it can be written as Q lambda Q transpose. So this theorem is also known in geometry and in physics as the principal axis theorem. The harder part is to prove that the symmetric matrices, what is the guarantee that the symmetric matrix would always have real eigenvalue? Because you saw that for real matrix A, it can have complex eigenvalues, right? So what is the guarantee that the symmetric matrix would have real eigenvalues and real eigenvectors? So, and orthonormal axis. So that is the harder part to prove. Okay. So how to prove that? So
Or we
we
can take a
need to,
general matrix and check it.
sorry?
I mean, to prove it, we can actually take a general matrix and check it.
Mathematical proof doesn't work that way. Like, you have to prove for a general case, right? General, what do you mean by general matrix? Like ABCD,
Yes, sir.
something like that. Okay. Okay, you'll understand, I guess. So the proof is, so let's prove first that all the eigenvalues of a real symmetric matrix would be real. Okay. So the theorem is all eigenvalues of a real symmetric matrix are real. So you'd prove it by contradiction. Okay. So in case of contradiction, proof by contradiction. So in case of contradiction, we first assume that lambda is a complex number. Okay. We assume the opposite of the theorem. So the eigenvalues or lambdas are, let's say, if one of the eigenvalue is a plus ib, then it will have another eigenvalue as a minus ib, right? So this is our contradiction. Similarly, for lambda, let's say we get one eigenvector with complex part x and another, the complex conjugate would be x prime. Okay. So from ax equals to lambda x, we get, it leads to let's say a x prime equals to lambda prime x prime, and we didn't use a prime with a because we are working with real symmetric matrices. So if you transpose the so let's say this is equation 1. So if you transpose this particular equation, let's say this is 2. So after transposing equation 2, we get x transpose prime a equals to x transpose prime lambda transpose, lambda prime, and there is no transpose over lambda because lambda is just a number, right? It is not a vector, not a matrix, so there is no transpose of just a number. So now, so this is our equation 1, this is equation 2, let's say this is equation 3. Now if you multiplying x transpose prime of both sides of equation 1, then you get x transpose prime, then ax equals to x transpose prime, then lambda x. And if we multiply x of both sides of this equation 3, then you'll get x transpose prime ax equals to x transpose prime lambda prime x. So as you can see in these two equations that the left hand sides of these two equations are equal. So we can say that x transpose lambda x equals to x transpose lambda x. So these right hand sides are equal, right? Now this equation can be written as lambda into x transpose to x equals to lambda prime x transpose x. So what I'm doing here is I'm multiplying x with its complex conjugate, right? So I think you remember from the characteristic or the properties of complex numbers that this x transpose x prime would produce a multiplication like this. So it will only contain real numbers, right? Because if you multiply two conjugates, you will get only real numbers. So there is no imaginary part here. So from this equation, let's say equation 4, we can say that lambda equals to lambda prime, right? So what was lambda? Lambda was a plus ib, and lambda prime was a minus ib. So this is only possible when imaginary part is 0, right? So this part is 0 and this part is 0 as well. So only possible when ib equals to 0. এখন I তো 0 হইতে পারে, so I cannot be 0 here, so definitely b is 0, right? So thus we have proved that the eigenvalues of a real symmetric matrix is always only this real number. And as the eigenvectors come from solving the real equations, so as the eigenvectors come from solving the real equation a minus lambda I into x equals to 0. So the x's are also real. So do you have any question or confusion regarding this proof? Okay, I hope this is clear because this is very intuitive. It only needs very preliminary knowledge of the complex numbers. So the second part is eigenvectors of a real symmetric matrix are always perpendicular. So this is the second part. So the theorem is the eigenvectors of a real symmetric matrix are always perpendicular. So how can I prove that? So our equation was a equals to q lambda q transpose, right? So these are orthogonal vectors, orthogonal matrices. So to make it orthogonal, we have to get orthonormal columns, right? Orthonormal columns inside this matrix. So how can I prove that the eigenvectors inside this Q matrix is always perpendicular? So this is the, so let's say, suppose ax equals to lambda 1x. So let's say this matrix A has two eigenvalues, lambda 1 and lambda 2, and two eigenvectors x and y. Okay, so this is equation 1, and we have another one, ay equals to lambda 2y. This is equation 2. Assuming lambda 1 is not equals to lambda 2. So we have two independent eigenvalues, and for two independent eigenvalues, we have two independent eigenvectors. Okay. So if we take so let's work with the first equation. So we have ax equals to lambda 1x. So if we transpose this, we have ax transpose equals to lambda 1x transpose. So let's multiply both of this equation, both part of this equation with y. So ax transpose into y equals to lambda 1x transpose into y. So we have x transpose a transpose y equals to lambda 1x transpose y. So from here, you can write x transpose a y equals to lambda 1x transpose y, because a transpose, so as we are working with symmetric matrix, so a transpose equals to a, right? So a transpose equals to a, so we can write this line. But from this line, but x transpose ay equals to, so from equation 2, we know that ay is lambda 2y. So x transpose ay can be written as x transpose lambda 2y, right? So the right hand sides are equal. So we can write that x transpose, the right hand side of this equation would be x transpose lambda 1 y equals to x transpose lambda 2y. So as these are scalars, we can write lambda 1 into x transpose y equals to lambda 2 into x transpose y. So when we first started the proof, we assumed that lambda 1 cannot be equals to lambda 2. So lambda 1 is not equals to lambda 2, right? So if lambda 1 and lambda 2 are not equal in these two equations, what might be the only case, or what might be the only reason that makes this equation make this equation true or correct? Can you guess?
Y equals to 0.
Yeah. So it is only possible when it is 0 equals to 0, right? Otherwise, these two values are different, so they cannot be equal. So there is only one possibility, that x transpose y equals to 0, right? And so this is proved. And what does it mean that x transpose y equals to 0? So these are vectors. So x is an eigenvector for lambda 1, and y is another eigenvector for lambda 2. So this, you know, that x transpose y, the two vectors, if the dot product of, so this is basically x dot y equals to 0. So that if the dot product of two vectors are 0, then those two vectors are perpendicular or orthogonal to each other. Okay. So yeah. So the eigenvectors of a symmetric matrix is or can be chosen orthogonal to each other. Okay. So finally, we have proved the spectral theorem, which is A equals to Q transpose, so Q into lambda into Q transpose. So this is the spectral theorem, and it has another property of this Q and Q transpose. So Q transpose Q equals to I, or the identity matrix. because this is an orthogonal vectors. That means these matrices are basically combination or the collection of orthonormal vectors or unit vectors. Those are perpendicular or orthogonal to each other. Okay. So what we can do is that we can write this A as Q1, Q2 up to Q2 matrix. So Q1 and Q2, and lambda is lambda1, lambda2, and this one is Q1 transpose, Q2 transpose. So this can be written as lambda1, Q1, Q1 transpose plus Q2 transpose. So this is a matrix Q1 into Q1 transpose. So this is column into row. This is also column into row. So when you multiply a column into a row, you will get a matrix, and it's a very special matrix, because if you could remember the for orthonormal columns, if you could remember the formula for projection matrix, it was Q transpose divided by Q transpose Q. And as I said, Q transpose Q is basically the identity matrix. So this is basically identity. So you have Q transpose, which is similar to these ones. So you can say that these are projection matrices. So we can say that this is lambda1 into a projection matrix plus lambda2 into another projection matrix. So you can say that every symmetric matrix is a combination of mutually perpendicular projection matrices. Okay, so projection matrices. So this is like another expression of the spectral theorem. This is very important. Okay. So there is another important phenomena with the eigenvalues and the pivots. So in cases of this symmetric matrices, the product of the pivots is equals to product of eigenvalues, and the product of eigenvalues, as we all know, is the determinant, right? So for symmetric matrices, it has so there is a beautiful rule with the pivots and the eigenvalues. Okay, and that relation is the number of positive eigenvalues is equals to the number of so if you have a symmetric matrix, any particular symmetric matrix, and let's two of the three eigenvalues are positives. So the pivots, there would be two positive pivot and one negative pivot. for that particular symmetric matrix. Okay. So there is one very special case, and that special case is A has, so A is a symmetric matrix. So A has all eigenvalues greater than 0. That means all eigenvalues are positive only if all pivots are positive. Okay. So this special case where all eigenvalues are positive. So in this special case, this matrix A would be called a positive definite symmetric matrix, or let's say matrix. Okay. So remember this term, positive definite matrix. Okay. So all these things were the preliminary knowledge that we'll be applying now. Singular value decomposition, or SVD. Okay. Singular. Okay. Singular value decomposition, or it is also known as SVD. Okay. So previously we started one kind of decomposition, and it was the eigenvalue decomposition, right? So decomposition is basically decomposition is basically breaking the matrix into smaller parts. So it was, so for when we had the so we are matrix, right? But this matrix was a square matrix. We only work with square matrices up to this point. Okay. So in real world, when you'd be working with real data, so it is pretty impossible that you'd always get a square matrix to work with, right? So data can come in any form. So we saw how important this decomposition is, right? So when you have a rectangular matrix, what can you do, or can you decompose the matrix in a particular form? So that's where the idea of SVD comes from. Okay. So the idea is a lot like eigenvalue decomposition, but in this case, the matrix Ax equals to lambda x, Ax equals to lambda x is not possible. This is not possible when A is rectangular, right? So for square symmetric matrices, we decomposed a particular matrix S as Q lambda Q transpose. So this S means square matrix. Okay. So for rectangular matrices, what we will do is that we would also divide it into three parts. The first part would be U, the second part would be sigma, and the third part would be V transpose. Okay. So this U is known as the left singular matrix, or matrix, and this is the right singular vectors, and this is not eigenvalue. This is not like lambda. This is sigma, and these are known as singular values. So it is a matrix with diagonal elements which are sigmas. So what are sigmas? We will know up to the rank. Okay. Okay. So how to get this? How to get A equals to U sigma V transpose? And like what is the usefulness of it? Okay. So as I said, A is not a square matrix, it's a rectangular matrix, right? But A transpose A is always a symmetric matrix and it's always a square matrix, right? So A transpose A is always a symmetric square matrix. So this this A might have an order of m into n, and this A transpose might have an order of n into m. So if you multiply these two, you'll have n into n, right? So if you have n by n matrix, A transpose A, if you have a n by n matrix, you can definitely express it as two orthogonal vectors, or okay, so you can definitely express it as V lambda V transpose, where these V are orthogonal. So as I said in the previous part, that if you have a symmetric matrix, you can express it as Q A equals to Q lambda Q transpose. So similarly, I'm calling this Q as V here. Nothing complex. So V lambda V transpose. So these are orthogonal. And we are working with positive definite matrices. Okay. So this lambda would be lambda I. So all eigenvalues would be 0. So we can only apply this SVD when this is a positive definite matrix. Okay. So in cases of positive definite matrix, the pivots would be greater than 0. And none of the pivots would be negative. Okay. And this is for A transpose A. And what about A transpose? So for A transpose, it would be an M by M matrix. And in that case, let's say we would divide it or decompose it into 3 parts, which would be U, lambda, U transpose. So we are calling this Q as U here. Okay. So what is our goal? So our goal is to decompose it. Our goal is to express an equation X equals to lambda X. X like we have to express an equation like Ax equals to lambda X. But as we cannot get eigenvalues or eigenvectors in cases of rectangular matrices, so we need to express a similar equation. So for rectangular matrices, what we're doing is we're looking for such an expression that AV1 equals to sigma 1 U1. Okay. So in words, so I'm trying to get orthogonal vectors in the input space such orthogonal vectors that if I multiply that orthogonal vector with a matrix, rectangular matrix A, I will get another orthogonal vector U1 with some scalar sigma 1. Okay. So for eigenvector, this equation would be AV equals to lambda V. So there would be same equation, same vector in both side of the equation. So AV1, as we wrote in the previous examples, that it should be AX1 equals to lambda 1 x1, right? In cases of eigenvalues or eigenvectors. So as this V1 is not an eigenvector because this A is not a rectangular matrix, is not a square matrix. So this is not an eigenvector. So you will get another vector U1, but that will be also an orthonormal vector. Okay. So for AV1, you'll get sigma 1 U1. For AV2, you'll get sigma 2 U2. And for AVR, we can only proceed up to the rank, right? So AVR equals to sigma R UR. So if I try to picturize it, what I'm trying to do here is, let's say this is the input space of V. So this is the input space and this is the null space of this. So, and this is another space, let's say this is U and this is the null space of U. So what I'm trying to do here is I'm taking different orthogonal vectors in this V1, V2 in this space V. Then I'm trying to multiply it by A. So multiply by A, and I'm trying to get another set of orthogonal vectors, U1 and U2, right, in another space or the output space, right? So if I try to, so there are number of equations up to the rank. So if I try to write all these equations in one sentence, it would be A, then all these input vectors V1, V2 up to VR stacked inside a matrix equals to this U1, U2 up to UR multiplied by sigma 1, sigma 2 up to sigma R, right? So this can be written as AV equals to U sigma. So if we multiply both sides of the equation by V inverse, we'll get U sigma V inverse. So this is identity matrix. So A equals to U sigma V transpose. You can write it because V is orthogonal vector. As I told you that these are basically unit vectors with perpendicular characteristic. So for orthogonal vectors, you can write V inverse equals to V transpose. All right. So this is A. So what would be A transpose A? So this A transpose A would be, so this transpose means V sigma transpose U transpose into U sigma V transpose equals to. So as U is uh, U is orthogonal vector, so U transpose U is identity matrix, so it should be V sigma transpose sigma into V transpose. So this has a very familiar form of Q sigma Q transpose, right? And if you also find out A transpose, it would be U sigma V transpose into V sigma transpose U transpose. So it should be U sigma sigma transpose to U transpose. So this has also the familiar equation of this one. So what we can say that this V is basically the eigenvectors of A transpose A, and this U is basically the eigenvectors of A transpose. So V is eigenvectors of A transpose A. U is the eigenvectors. Okay. Eigenvectors of A transpose. And what you'll get in this sigma transpose sigma or sigma sigma transpose. So what you'll get here is that you'll be multiplying this sigma 1, sigma 2 up to sigma r in with its as it is a diagonal matrix. So the transpose would be same, right? Sigma 1, sigma 2 up to sigma r. So this would be basically squared. So sigma 1 square, sigma 2 square to sigma r square. So this sigma square is basically the eigenvalues of A transpose A and A transpose. So how we can find it out? Like when we do working with real math, how we can find this V and U? So previously we worked with these equations. If you work with this, so we had A V1 equals to sigma 1 U1. So from this, we get U1 equals to A V1 divided by sigma 1. And we had A VR equals to sigma R UR. So from this, we can get UR equals to A VR divided by sigma R. So what you can do, first of all, you can get this V matrix from A transpose A, then using this equation U1 up to UR, you'll get the U, capital U. So then we can easily find out A equals to Q sigma V transpose. But there is one question. If we choose these V's as the orthogonal orthogonal vectors or orthonormal vectors. So what is the guarantee that this U would be orthonormals as well? So we can check it out. So U1 transpose U2 would be a V1 divided by sigma 1 transpose this equation into a V2 divided by sigma 2. So if you simplify this, it would be V1 transpose A transpose into A V2 divided by sigma 1 to sigma 2. Now look at this matrix, A transpose A into V2. We told you that this V1, V2, V3 are basically the eigenvectors of A transpose A, right? So A transpose A, V1 would be lambda 1 V1, right? Or in this case, it is not lambda, it is sigma 1 square, because the sigma square is basically the eigenvalues of A transpose A and A transpose. So A transpose A V1 equals to sigma 1 square into V1, because V1 is a eigenvector of A transpose A. So what would be A transpose A into V2? It should be V1 transpose into so A transpose A into V2 would be sigma 2 square V2 divided by sigma 1 into sigma 2. Then if you simplify it, you'd get sigma 2 by sigma 1 into V1 transpose V2. So as I said, we choose these orthogonal vectors. So as for orthogonal vectors, it would be 0. So the whole part would be 0. So U1 transpose U2 is equals to 0. So these matrices or these vectors would be orthonormal vectors. Wait. So think about the geometry behind this for a second. So if you multiply a set of vector
Hello, sir.
Yes, can you hear me?
Yes.
Can you see the
Yes.
screen?
Yes.
Okay. So let's say you have so you have x, right? So you're multiplying this x vector with, or let's say a set of vector x with this particular matrix A. So let's say you have x This is X, these two vectors, X1 and X2. So if you multiply, so first you're multiplying with V transpose. So V transpose is basically an orthogonal vector, right? So what does or orthogonal matrix, sorry, orthogonal matrix. So what does an orthogonal matrix do? So if you multiply a set of vectors X with an orthogonal vector or orthogonal matrix, what would happen? Rafio?
Hello, sir.
Yes, if you multiply a set of vectors X with an orthogonal matrix, what would happen?
Uh,
Forgot the concept of orthogonality. Okay, so take this as an assignment. Okay, so if you multiply this, you have this matrix A, and it is divided into three parts: U, sigma, and V transpose. So if you multiply X, any set of vector X with these two part of the equation, what would be the pictures? What would be the pictures here? Right. So this A can be written as U, then sigma, then V transpose, right? So let's say this U is a M by R matrix. So U1, U2 to UR, then sigma. So sigma 1, sigma 2 up to sigma R. So M by, this is M by R. So this should be R by R. And the last one would be R by N. So V1 transpose up to V2 transpose up to VR transpose. So this sigma comes in such a form that the sigma 1 is always greater than or equals to sigma 2. Sigma 2 is always greater than or equals to sigma 3. So, and the last part, sigma R, is always greater than 0. Okay, because we are working with positive definite matrices. So if you multiply these three things, you'd get U1, then sigma 1, then V1 transpose, plus U2, sigma 2, V2 transpose. But as you can see that sigma 1 is always greater than sigma 2 in most of the cases. Sometimes it might be equal. So this part or this element will have always a greater weight than the other elements here, right? And the least important element here that is like very close to 0, it would be UR, sigma R, and VR transpose. So considering the weight of this element, we can easily neglect this, right? So this can be labeled as the principal component of this principal component. So this concept is used in image compression. Let's say you have a very big image, right? You have the very big image. So you might know that images are basically a matrix of pixels. Okay. So let's say you have very good details here. You have very good details here. You have very good details here. But there is not much details at this part, at the lower part, right? So by using this SVD, you can get the principal component, and you can easily ignore the auxiliary components that are not very important for the image. So if you just preserve the principal components, most of the details are preserved, but after SVD, you might lose some details around this part, but you'll get most of the details that is needed by applying this SVD and getting this principal component, right? So this is used in image compression. So similarly, in data science, you have a very big matrix A with a lot of noise, lot of signals, and many other components. So with this SVD, you can divide it into decomposed part, and you can easily, so let's say this is noise, this is signal, and let's say this is buffer. Okay. So you need to extract the most important part of the matrix. So by using this principal component, you can extract the most important signals or most important noise or most important buffers from the matrix, from the data matrix A, right? So as long as you can divide the matrix by SVD, you can analyze the matrix into smaller parts, and you can extract the most important informations out of it. Okay, so that is the primary use of SVD, and that is used in many machine learning techniques like principal component analysis, signal processing. You'll see a lot of use in your DSP course, digital signal processing.